Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This weekend's been kind of weird for me because it's the first weekend in about a month where I haven't either been at a demo party or been preparing for a demo party. And my body has seemed to really know that and just make me sleep this whole weekend. So all I've been doing is just been like laying down, playing video games, playing Nier Automata. That game is awesome, actually. It's been really fun. Just watching a lot of movies. I watched Ghostbusters. I watched Ghostbusters 2. I watched Stranger Than Fiction. And I watched a lot of How I Met Your Mother. I've been having a good weekend, but it's been pretty low-key. Whoop, sorry. So I didn't really know what I wanted to do on the stream. I thought we would do something a little more low-key, because my brain doesn't really want to work on stuff. But, last weekend we put out this really small demo here. Let me actually restart this. Just running this in an emulator here. We can just do this. I think that broke stuff. Oh, it actually kind of worked. Let me do a restart here. Basically what this is, it's a really small demo that was done by, so I did the code for this, and then Flipside, aka Alex of Pegboard Nerds, did the music here. So basically what this was that Alex did a SID cover of this Pendulum track, a really nice one, and then he also did kind of a version of the album artwork here. And he messaged me with basically those two things, a work in progress of the art and then basically the SID that you hear now. And he was like, yeah, so I kind of just want to make this little thing for this track with a scroller and stuff. And I was like, okay, cool. This is a good opportunity for me to play with more C64 hardware effects. So this was maybe 3 weeks ago. It was, I can't remember if it was right before Evoke. Must have been. And I just told him, yeah, this would be cool. I don't have any time to work on this until after Evoke. Whatever. Over the 2 weeks after Evoke, just kind of putzed on this, did most of the work. Would have been 2 weekends ago, so the week before Data Storm. That's where I was last weekend, by the way, Data Storm in Gothenburg, and that was basically an old school party, particularly Amiga and also C64. And so it kind of, the timing kind of worked out because he had made this stuff, and then we could totally just put out this little thing, and I could use it as an opportunity to play with more hardware tricks and kind of do, you know, some nice stuff with the packaging here, and then he got to release the track to an actual audience that would actually hear it and appreciate it, rather than just like putting it out on Facebook or something. So yeah, it was just something that happened totally naturally, and it was really fun. And so I thought, since I've been thinking a lot about C64 lately, especially the hardware, after we did the 4K for Solskogen, at Solskogen, actually, someone pointed me to a particular piece of documentation, which is literally just called the Vic article. Now, the Vic-II in particular is the video chip in the C64. But this particular article was actually released in like 97, and it has a lot of really good information about how the internals of the video hardware works. And even though I had used a particular hardware trick in that 4K, I didn't really understand it to that low, like that much of a level. That good of a degree, but more recently, I've actually been able to do that through reading this article and a couple other things. And that's been really, really fun, so I thought I would just kind of take a look at this and tell you guys how this scroller works, because there's actually some kind of interesting hardware tricks there. And then kind of segue into talking more about the hardware generally, because I thought that would just be fun to kind of brain dump what has been kind of stewing in my head a bit, and what's kind of been making me want to do even more C64 stuff lately, just because I've been, again, just been thinking about how this hardware works, and I thought that could be kind of fun. So I think that's what we'll do on this stream. Nice and low-key. Should be pretty cool. By the way, how's the music volume, guys? Is that too loud? Like, if I just continued talking while this was playing, would that be an issue? While you guys answer that, while we wait for stream delay, I'll say hi to you guys in the chat. Studio C, Soding, Kluwash, John Hunter, Metal Voids. How's it going, guys? This are used. Cool. So what I have running here, by the way, this is this C64 debugger that I've mentioned on a couple other streams as well. Let me try to find a view that's actually useful here. So there isn't too much going on here. I mean, the main parts of this is there's music playing, and there's a couple things to do with that. There's the picture in the background, which is actually made from 2 layers. Let's see if I can get... yeah, here's a good view of this. So the background is just made from like a static bitmap, multicolor bitmap in particular. Let me actually... I wonder if I can move my face here. Hold on a sec. Because there's some stuff down here that I want to show. Down here. I don't want to just move my camera because I want to be able to put it back there later. So we'll try this. Hold on. Alright, we're just gonna move me. It's gonna be fine. Whoa! I'm over here. So basically there's this background image. It's a static image. There's these sort of wipe color fades, but that only changes the color values of the picture. It doesn't actually change any of the picture data itself. So this is a static bitmap. You can even see where it is in memory. At 6K, and then at 4K we have the screen memory, which is where the colors are going to come from. Ignore the flickery crap that's going on. There's just some things this debugger is trying to show me that aren't very relevant. And then you also have these stars, which are just sprites here. And those are also basically static in memory, except that I changed the sprite pointers. In fact, you can see them just increasing here. And they just cycle through like 8 images each, I think. And it's really that simple. So that's really all that's going on in terms of the like image background here. And then again, every so often I have this fade routine that just goes through and changes the colors. The interesting thing here visually, though, is there's also the scroller, and you're not going to see it work properly in this view, particularly because of the way it works. It doesn't actually do anything that crazy, but I kind of like the routine that I made for this, so I want to talk about it. See if I can get a good way to show this. I don't think there might be one. But anyway, so the way that this works is I do something called FPP. Now I've mentioned FPP before. It basically stands for flexible pixel position, and it's one of those sort of standard, like, I wouldn't call it a hardware trick because it's really not. It's really an application of a hardware trick. So basically during this portion of the screen, I have 8 different graphics lines that make up the different 8 pixels of the scroller. So the scroller area is normally 8 pixels high. You can see there's this border and like a thin black line here. That's actually where it starts. So there, and then there's a 24 pixel high area, including this top black line and this bottom black line here, where the scroller is displaying. So that's normally the height of 3 character positions here, 3 character rows. But I do a hardware trick that does a couple things. So the hardware trick, what it actually does, and it's the same one we used in the Plasma and Makeshift. And there's a reason why I use this one, and I'll get to that when we're talking about this a little later. But basically every, like the character row here, right at the end of the last row, I actually tricked the hardware to display the same text row again. Now it doesn't look like that's what's happening, right? Because you see a bunch of stuff bouncing and a bunch of the lines actually changing. But that is actually what happens. So that's sort of that's the actual hardware trick we do. The other thing is that every scan line, I also change which character set it's pointing to. So basically, I take the font, and I can show you guys kind of the code, which might help clarify what's going on here. So we have the original font. I'll pull up the file for that as well. That's kind of cool. Yeah, glad you like the Sid, Studio C. I think it's a really cool cover. here. So this is what the font image looks like. Just zooming in here. It's just straight up black and white image. And this is basically converted in the graphics format, which is a really simple format where you have each of the characters is 8 bytes because it's 1 bit per pixel, and it's 8 by 8. So there's 8 bytes here, and then 8 bytes here, and then 8 bytes here. So I have a small Rust routine to convert that, which is here. Here, convert the font. So it's really, really basic. And then that's included here with some ink bin down here somewhere. Here, import binary here. All this is managed by this makefile thing. By the way, I did make this source open source. Let me link that really quick. I don't know if you guys will be able to follow along because I won't really go through it line by line, I think. But just so you guys kind of have some bearing. But what I do is I take that original font and in the format that I described, and I actually unpack it into 8 different fonts. I don't think we'd be able to see this in the debugger because it would happen so quickly. But basically what I do is I have in the last bank of memory, so let's go ahead and look at this, this one. So there's different banks of memory. Basically, if you take the whole area here and divide it into 4 banks, you'll have one that starts here-ish and one that starts here-ish. So it's bank 3, 2, 1, and 0, and this is actually memory location 0 and memory location FF down here. So bank 0 is actually the last bank in memory, and bank 3 is the first bank. It's kind of weird that it's like that, but it is. But in this last bank particularly, it might be hard to see, but you'll notice there's a lot of these sort of bars here. And there's some extra stuff showing here because there's some other things we're changing too. But most importantly, these bars here are actually copies of the font, basically. But they're each copies that are kind of interesting. So the first one is actually this, like, each one is the font repeated. There's 8 of these in that last bank. And the first one only has the top line of the font repeated 8 times. The second one has the second line repeated 8 times. The third one has the third line repeated 8 times, and so on and so forth, till you have all 8 of them. So what that allows us to do is at any time within this area, because we just have it repeat the same character row over and over again with the same character indices, by switching the character set at each line, we're able to select which of the 8 pixels in the font that it will show, if that makes sense. So we can kind of think of it by like having this scrolling graphics here, and then we can choose which of the 8 font lines to display there. Additionally, every line I also change the background color, so I actually have the font inverted. This is actually why it's black on white, because it's not the black pixels that you're actually seeing in the font, it's actually the white pixels, and then it masks out the background color, so whatever's black here, you'll see the background color through it, and then the foreground's actually black, in this case here. And so by changing the background color every line as well, we can change not only which line are we seeing here, but also what color it's going to be, right? That kind of makes sense? So from there, I just built that kind of display routine. It's just this unrolled loop here, where every line, it reads from a table that has the character set values, it reads from a table that has the background color values, and just stores them into those registers. And then it does wait a little bit and then do this hardware trick, and then wait a little bit and start over. And so once we have that, then we basically have these 2 tables. One of them describes which line of graphics from 0 to 8 that we're going to display, and the other one describes the background color, which is just a 4-bit value. And then for one of the 16-bit colors, or sorry, one of the 16 colors, 4 bits. And then from there, I just fill that with different effects, and then also have this little transition effect where it just makes the colors black, sort of fades in and fades out, kind of pinches on the thing. But that's really all that's going on to make this effect. There's that harder trick that just repeats the rows. From there, we can change which line we're displaying by displaying a different character set, which has kind of been baked by the different lines of the font, and then we can change the color as well. So then I just fill those tables. Also, the other thing this display routine does is it actually clears those tables as well for the next frame as it displays. That just makes this a little more convenient because we have some extra cycles within this loop that has to be particularly timed to change some things during the scan line to make this harder trick work, and I'll get to how that works. It's actually pretty interesting. And then we just fill it with stuff. So I have here There's a static scroller, which just goes through 8 lines starting at about the middle, and then just, yeah, puts in increasing index in all of the lines that it's actually going to cover, and it also puts white in the color table for those lines. That's how we get just the static one. There's one where it moves, which is the same thing, but it has an offset here that's calculated with some sign table crap. We have this mirrored one. This is the repeating one, which is where we just put in all the lines in order and then just let that wrap around with 3 bits, but with an offset that's some sign table stuff. And then there's a color buffer as well. This is that dynamic one that I mentioned here. We'll get to the mirrored one after this, which is actually my favorite. I can pause this. And so the mirrored one, it just takes it and it draws in. So again, there's these 2 buffers. One of them is the color buffer and the other one is the line index buffer. It just fills in the line index with 0 to 8 here, and then 0 to 7 here, and then 7 to 0 here. And it fills these ones in with white and these ones in with gray. It just does that as 2 loops. So there's the white one, and then there's the gray one here. Like, really basic once we get the display routine working. But what was really nice about this to me was that like I said, since doing that 4K makeshift and reading more about the hardware, it was fun because I could kind of, like, I knew I wanted to do this kind of display routine where I wanted to be able to pick which line we're displaying so I can do stretchy stuff like this, and then also change the colors just to make it really dynamic. And then I was able to kind of go through how the hardware works and kind of pick the trick I wanted to use. Like, there's a reason why we use this same one again. It's not because I was that familiar with it, but it was because one of the properties it has is that when you stop doing the hardware trick, the video will continue to scan out the video hardware will continue to scan out graphics normally afterwards, which is really nice. We also can just start doing it basically right away, right at the beginning of the area here, which is really nice. And it also allows for a lot of cycles per scan line. This trick we really only pay or yield some cycles to the video hardware on the very first line where it's reading all of the character indices, and then the hardware will not do that as long as we do this trick for the rest of the display area, which is kind of cool. So there isn't much more to say on that stuff, probably. See if we can even see some of this. This display in this debugger gets kind of weird here, but I will be able to more easily describe how this trick works after that. But yeah, I mean, that was kind of what was really nice about this for me, was that I was able to kind of get sort of practice with applying these hardware tricks, and this application of this trick, even though it's the same trick as Makeshift, I feel like it's a lot cleaner because it was a bit more focused. Like we did in Makeshift, I kind of just played with stuff until it sort of matched what that one Enter Disgrace Plasma was doing. But in this one, I had sat down and was like, okay, I need to do this trick, so every 8 lines, I only have to do these 2 things, and then it will just work. And I could kind of build it around that without using a reference for the actual implementation. And it totally worked, and so I was pretty happy with that. The last thing, though, before I move on and just talk more about the hardware, I guess, is the actual fades that happen on the screen. And so you can see it kind of scan out like that. They happen, I think, every 512 frames it'll do that, just because it's easy to count up 8-bit value a couple times. And the way that they work is they're actually pretty simple. I just take, so each of the 8x8 blocks here, these sort of character indices, you can have a separate, basically 3 separate colors, 3 unique colors. So the whole screen has black as sort of a main color, and then you can have 3 different colors in addition to that in this particular bitmap mode per 8x8 block. And so all I do is I just have some tables for the first and second color because they're stored in the same place, and then another table for the third color for each transition. I can kind of show what that looks like. That's these guys. So there's the screen mem, which takes care of 2 of the colors, and then there's a color mem, which takes care of the third color. And this is the colors basically fading out and then actually fading in from right to left, and there's a reason why I do that. So basically I take an index on the screen that normally starts like out here, and it scans all the way out to about here. And then from there and like the next 8 characters, if that's within the range of the screen, as I kind of scan this out, then I just look up the color in that buffer and just store it. So the code is fairly simple. It's right here. So I take, frame counter, and then based on that, I will figure out where we are along the screen. If it's within the screen range, then I just write that same value for all of the screen mem all the way down, and same with the color mem all the way down for the column. So I'm basically changing the color per column, even though it has to be done per character. So I use these big unrolled loops that just write the same value 25 times. They skip over the parts where the scroller is, because there we need that to stay black in the color memory, because we're going to change the color by changing the background. There, actually, when it's scanned, you can kind of see that a little bit better. But of course, you're seeing the background colors change when I hover over here based on what it was for that line. So it's kind of funny. But you can kind of see how it scans through the color memory when it will shift. See if we can see that. There it goes. So it literally just writes all those values from this table, or from these tables, based on those offsets. And that's why it kind of fades in from right to left, because it's only going to write that one area of the screen. And because it scans from left to right, it's going to write these first and then these. So it's kind of a basic routine, and these tables were a pain in the ass to do by hand. I shouldn't have done them by hand, but I did. Just sitting there at Datastorm on Friday. It was pretty easy, and then I can also fade the sprites. I do them all at once when the colors shift. And I use those same tables, actually, to do that. So if you can see up here, when the colors change again, you'll see them just kind of fade out at one point and then fade back in. So they use the same tables, but a little bit of a time offset. That's really all there is to this intro. The rest is just kind of putting it together. It's packed with the same packer that I made for the 4K. The thing clocks in at around 12K or something. Wasn't really trying for any particular size, but this does use about 30K of memory uncompressed, and that was a bit of a long load time, actually. Like when you actually start it on the real machine. So I thought the compression would be kind of a better trade-off, even though it takes a couple seconds to decompress, which isn't too bad, because I added a little like progress indicator, at least that it's a liveness indicator, not really progress, but that it's actually changing stuff. I'll just show that here. Whoops. Hold up. Hard reset, please. Okay. I'm gonna restart this. But yeah, so when it loads, you have this indicator down here that says doing stuff. And then it starts up. And then there's nothing special about the intro when it fades in either. It's just that this first table has black, and the whole color memory is initially black, and then it will also offset the scroller just by adding a bunch of spaces at the beginning of it. And all that's just to kind of, like, there's a sort of sweep fade in with the music, and I just kind of tweaked that till it matched, and then that's about it. And there's really not much more to it. So again, all the code's on GitHub, so if you guys want to check that out, go for it. But yeah, I just kind of want to talk more about these hardware tricks and the way sort of the Vic hardware works, because it's actually like a lot more simpler than I realized. So let me find this Vic article, and then I'll try and see if I can find some basic stuff about the hardware, because this Vic article is kind of a dense read, I should say. This is the original text version. There's also a PDF version, which is a little bit nicer, actually. A bit nicer to read this one. Let's see if this has some nice pictures that I can use to give you guys sort of like a crash course into this. Because it goes in really deep, and I only want to talk about certain parts of this. Okay. So I think this is a pretty good place to start, is if we just look at this. Hold up. I thought that would be quieter. I'll just close this. So particularly, the C64 draws graphics. Like, it has sort of different hardware units, and there's actually a nice block of the hardware units up here. Let's see if we can zoom out a little bit here. There's a clock generator here, something that generates refreshes. There's some interrupt stuff. We really only care about sort of the border unit here. There's a sprite unit here, and then there's a character unit, which is kind of all this stuff. I really only want to talk about the character stuff at the moment. But to kind of ground that information, we have to kind of look at the frame like this. So the frame looks roughly like this. There's like a character area, or this is the display window it's called here. And then there's the border areas around that. Basically, the display area is 320 by 200 pixels in area, and it's meant to be sort of centered on the screen. The reason why a lot of old computers had a lot of border area like this is because a lot of these were meant to work with televisions, which at the time could have a lot of overscan in different areas, and they wouldn't be that consistent. And so having a border here would actually sort of make sense in terms of making sure that the display window would always be visible on your TV in the early 80s. And the graphics themselves are really made up of three things. You have the character graphics that's displayed here, and even in the bitmap modes, I find it still helps to think of those as character graphics, because with the exception of the fact that it reads memory from a couple different places, it really acts quite a bit the same, depending, like regardless of the graphics mode. There's a couple internal registers that scan out just the same no matter what. So there's the sort of character graphics. There's the sprite graphics, which are these movable blocks that you can have up there. And that's a whole other can of worms, but I've been mostly looking at the character graphics recently, so that's mostly what I'll talk about, I guess. And then there's the border graphics, and the border is really just a solid color. But there are some tricks about how it works that allow you to basically turn off the border, or rather keep the border from turning on, because you can actually skip the condition. You can have the hardware skip the condition that turns it on, which is kind of funny. But this 320 by 200 pixel area is made up of 40 by 25 characters. There's a way where you can select a different amount of rows or columns that the hardware will display, and that really all it does is it just kind of chokes up on the border area. So the border will start a little bit later and end a little bit sooner. Either the left and right or the top and bottom, which are independently controllable. And in fact, that's actually how you disable the border from turning on. You actually turn it to the smaller display area, and then you wait until it's displaying within those last few pixel rows here, and then you change it to, you have it be the taller one, and then you wait for it to be displaying this last one, and then you switch it to the shorter one, which actually makes the hardware skip turning on the border, because it thought that it would have done it here, but it's doing it here because it's the taller one, and then it'll just continue displaying graphics. Of course, the character display outside of the display window goes into something called idle mode, so it won't actually display anything very useful, except there is actually something you can do with that, but it's not much. But the sprites will actually work down there, so if you ever see stuff in the borders, mostly sprites, sometimes a clever application of what the character graphics still does out there, but mostly sprites. But in terms of the actual hardware implementation of this, there really isn't that much going on. I mean, when you're talking about how hardware will sort of scan out a display like this, you basically kind of look at one scan line at a time, because the rest of it kind of is just, you do a bunch of scan lines, a certain number of those in a row, and it will just scan out a 2D frame like that. But it's really just stacking the sort of one-dimensional things that happen on a line. And particularly, there's a few really interesting things here. Where should I describe some of this? A lot of stuff is being described here as I'm scrolling through this, but I kind of want to simplify this because there's some really interesting stuff here. Particularly this section here, which describes... through reverse engineering, these guys who wrote this article basically figured out how the VIC should work internally. It's all speculation, but based on their findings here, this is how the modern emulators are implemented, and it totally seems to match up. It's like they observed a bunch of the actual behavior of the VIC by the ways that you can interact with it normally, and then through Occam's razor came up with this kind of inner workings of it, and it totally seems to hold up. So let me find a picture here that I can use to sort of describe this. By the way, guys, feel free to interrupt me whenever. I'm just talking about this stuff because I think it's cool, and I've been thinking a lot about it lately, so more of a brain dump. That's not a very good example. I kind of want to find some text stuff. Maybe if I can find some pet ski graphics. That would be cool. This is quite nice. John Hunter, whatever happened to Commodore Basic V1? No idea. Hey, Ska. Just hanging out, talking about C64. So let me pull up that emulator as well, because this will make it a little bit easier to describe what I want to describe. So this is the sort of basic interpreter here. Really, the only thing important here that you have to realize is that it's just like I mentioned earlier, a bunch of little 8x8 blocks, which we can call characters. And there's 40 of these in the width and 25 of these tall. And then, of course, we have the border and the sprites, but I just want to talk about sort of the character graphics for now. And so the reason I bring this up is that the way the hardware actually displays this is it'll basically have the character unit in idle mode, which means it's basically displaying crap until this display area starts. And at some point within this display area, it's going to start actually scanning out characters. Now, there's actually characters all the way up here that you can't really see because of the way the Commodore Basic thing is set up. But basically, there's something that happens during the display area that starts the display scanning out one row of characters, right? Now, this happens every 8 lines, and I'll get to what this is called, why it's called that, and why I don't want to say the name right away before you know what it is, because we're going to talk about a better way to understand it than calling it what it's actually called. Calling it what we usually call it. But something happens that will start the character unit displaying one row of characters, right? And then 8 lines later, after it has displayed the first row of characters, it will actually turn its, like on the 7th line, at the end of the 7th line, it will actually turn itself off and then go out of display mode. But then on the next line, because it's every 8 lines this condition happens, the character display will start again, and it will display the next row of characters. And then at the end of that, it will turn itself off. And then that will keep going until on the last one, on the 7th line of the last row, so that'll be at the end of this row. At the end of the 7th line on the last row, it will turn itself off. And then that condition that told it to start again will not happen because that doesn't happen outside of the display area. And then it will basically continue in that idle state until the next frame starts. And what's kind of important here to realize is that what's interesting about the hardware, and this is kind of what I recently realized through reading this stuff, is that it doesn't, the video hardware doesn't sort of scan out many characters of text. The hardware, what it really does is it scans out one row of text, right? One row of characters. And it just so happens that the hardware will do that, like the condition that starts the hardware doing that happens many times throughout the frame. And also at the end of the line, on the 7th line, not only does it turn itself off, but it also has this sort of feedback mechanism that increases the read pointer, which is why the second time it starts displaying characters, it will display the next row and the next row and the next row. Has this been confusing yet? I mean, it should be fairly basic, but there's kind of a certain interesting way to think about this, which is why I think that this is cool. Exactly, Ska. Oh, man. So all I'm really trying to say, I'll say this one more time, is that the hardware scans out the whole screen really by just scanning out one row at a time. The hardware only knows how to scan out one row, and it will just, there's a condition for it to start doing that happens to happen many times, but that's all it really does. Hey, look, Semtex. I don't know if I said hi already. So even in, so this is an example of Petsky graphics, and you can see it's basically the same thing. There's some JPEG artifacts here, but this is supposed to be the same color. I mean, this is the same thing. It's just drawing different character indices. I'm guessing this light blue color is sort of the background color in this case, or actually it's probably this gray. And then we have another foreground color, each of these. Not too important, but it's another form of the graphics that's kind of displayed the same way. And even if you look at the C64 bitmap modes, they basically work the same. Let me find a good picture. This picture's insane, by the way. Just in terms of how technically amazing it is. But if we were to break this down into 8x8 blocks, also some JPEG artifacts here. Whatever. We would also see sort of the same thing, that each one of these can be kind of thought of as a character. Again, there's a little bit of different reading around that the hardware does, but it's basically the same thing. It will display one row, and then the next time it will display another row, another row, another row. So one of the things that's interesting here, something's going on here. Got it in some kind of weird state here. So the other thing that this hardware has is it actually has some scroll registers. And the scroll registers will only shift the screen either down or to the right from 0 to 8 pixels. Now, by default, it's actually 2 pixels shifted already, so we would have a little bit to the left and a little bit to the right. In fact, let me look up the... or actually, no, that would be a pain in the ass. I'm not going to do that. But what's really interesting here is if we consider just the vertical scroll, we can kind of ignore the horizontal scroll. All the vertical scroll actually does is, so remember I told you that the video hardware just sort of scans out rows of characters. All that scroll is doing is it just delays or makes it happen sooner that condition that starts a character row display, right? So if we were to scroll the screen up 1 pixel, all that would do is make the character display start 1 row earlier. And then after that, everything's going to be the same. So 8 rows after that, it's going to start another row. 8 rows pixels after that, it's going to start another row, right? So it turns out we actually have a name for this condition, right? And we call it a bad line condition. And the name is kind of backwards from this because every 8 lines, like I said, the hardware is going to draw out 1 row of characters. So every 8 lines, what it actually does is it has an internal register that's 40 sort of cells wide, and each one of those cells is actually 12 bits. Now the lower 8 bits are taken up by the character index for each one of those. So there's one for each of the 40 positions on the row. And then the upper 4 bits are taken up by the color information. So there's 16 colors on the C64 that can be represented in 4 bits. So you basically have an internal register in the hardware that for every character row that it will display, it first needs to read in all of the character indices here and all the color indices here. Now, normally, the there's so much to describe here. I'm just realizing that I just did not think about when I wanted to talk about this stuff. But it's interesting to describe. So I might lose you guys, but I hope I can sort of talk about what I want to talk about. So there's only one data bus on the C64. Really, I mean, I think there's a couple I think it's a 12-bit data bus and a 16-bit address bus, where the video hardware is actually only hooked up to 14 bits of those 16-bit addresses, but it's hooked up to 12 bits on the data bus, but then the CPU can only see 8 bits of the data bus. This doesn't matter. I'm just talking about this for my own sake, but the important thing here is that there's one bus, basically one master bus, and so the CPU and the video hardware have to actually take turns using that. Otherwise, they'll step on each other's toes. Now, normally during character display, or any graphics display, the video hardware will not need to impede on the CPU in terms of accessing that bus. There's 63 CPU cycles per scan line. And as it turns out, because there's only 40 character positions here, if the if the video hardware were able to read like the graphics, so the actual pixel data here, which is something we call G-axis, which is when the video hardware needs to look up graphics, it can actually look up all 40 of the lines. So every pixel line here, there's 63 cycles, and it can use 40 of those to actually read in the actual pixel data here. So remember, each one of these would be 1 byte for the 8 pixels here. 1 bit per pixel in this case. So for every pixel line, we would need to read 40 bytes. However, the issue is that you actually need to read sort of 2 bits of information per character row, because you need to not only be able to read the actual graphics here, but you would also need to be able to read in the character indices, which would determine where you're reading the character graphics from. So that would end up coming in at 80 bytes, except that they would actually be 12-bit values because of the color memory as well. And there's less than 80 cycles per line. There's 63 cycles per line. Now the nice part is that there's the sort of main clock of the system. The video hardware actually runs at 8 times the clock of the main system, and the reason is because it needs to scan out 8 different pixels for every CPU cycle that the CPU has. So every CPU cycle is 8 pixels. So that's why we can get 1 byte per every 8 pixels and read those out. So under normal operation, when we can actually split this up, is sort of the way to think about this. So we're thinking, hold on, I totally have not prepared for this, as you can see, but I just find this interesting. I want to talk about it. So we can actually split this up, because for a character row, like if we're looking at a pixel row, we have to read 40 bytes of data because we have to display the different pixels for each of those positions. But if we're looking from the perspective of a character row, we still need to do 40 bytes per, the video hardware still needs to access 40 bytes per pixel row, but the character indices are going to be constant for those 8 lines, right? For those 8 pixel lines. For that character row, the character indices here are going to be constant, and it's just going to read different pixel data for every scan line. So what it does is when it's reading the pixel data, there's the clock that runs where the CPU runs on like the rising edge, and then the video hardware actually runs on the falling edge. And so it can kind of go back and forth between using the bus for the CPU and using the bus for the video hardware. And that gets us enough bandwidth through there so that 1, we don't interrupt the CPU, and 2, we get to read all the graphics data we need to per scan line here. Now that covers the graphics data, the actual pixel data here, which is what we call the G-axis because it's graphics data. But it doesn't cover the C-axis, which is what we call when it needs to get the character indices. And it actually gets the character and the color indices because those are also constant. It gets those at the same time, which is why it has a 12-bit bus. So on those lines, we still need to read the actual pixel data for all the graphics, right? Because it's the top line of the character. But at the same time on those lines, we also need to be reading the character indices. So what the hardware does is on like the cycle before, I think it is, before it's going to read all the G-axes, it actually locks the CPU out, and then it takes up 40 cycles from the CPU, where the CPU would normally be able to get to use the bus. It actually takes over that, and so then it alternates reading character indices and then the pixel data for that character index over and over and over again, if that makes sense. So it kind of interleaves those, whereas normally the CPU would be using the bus during that time. I think the Vic article goes over this, maybe with a picture, but I think it's not very nice pictures, actually. They're the kind of pictures that are very accurate, but would kind of take a lot of, I think they'd be a little hard to read. But does it kind of make sense what I'm saying? Because then you have more than enough time for the video hardware to read all of its data, but only because it's blocking out the CPU. And it actually has to, it sends a like bus not available signal to the CPU, I think 3 cycles before it starts actually taking over the bus for during the CPU time. And it does that because I think the longest instruction on 6502 is 7 cycles, but I think that's the longest period between, I think the most time the CPU will actually spend doing consecutive bus accesses is 3 cycles or something. But really what I want to describe is that every 8 lines, when it's going to start displaying a new character, that first line that it does that, it needs to do both C accesses and G accesses. So we're going to lose from the CPU's perspective 40 cycles because it's going to be spent reading graphics data. But then the other 7 lines, it's just going to be reading graphics data transparently, and we're not going to see the difference, and then it's just going to display this until the end of the line. So I'm probably losing you guys even more. I wonder if this stuff is actually covered in Michael Stiles' Ultimate C64 talk, because I don't think it ever went into this much detail, especially with these 3 internal registers, which is kind of what I want to where the meat of this actually is. VC, VC base, and RC. Because I had like this mind-blowing moment at one point where I was kind of understanding finally how all this worked, and then I would just go through this list of hardware tricks on the C64 and be like, oh yeah, that's because this register gets held at this value because you missed this timing window and stuff. It was pretty crazy. But at some point I might just have to make a presentation about this stuff because I'm really interested in it right now. Yeah, I guess there's some cache lines that need to be swapped out. Love like Semtex. So let me just kind of continue and see if this starts to make more sense. And we'll use this as practice. If I ever make a more proper presentation, I'll know how not to describe this stuff. But anyway, the reason I brought that up is because on the first line of every character row display, because the video hardware has to use those extra 40 cycles the CPU would normally have in order to read the character indices and the colors for each of these. We call that first pixel line a bad line because we get about 40 cycles less from the CPU's perspective than we would on the other lines. On the other lines, it's 63 cycles on PAL, 65 NTSC, but we're just going to look at PAL. And then, yeah, we have 40 less the first of every 8 lines. So every 8 lines we would historically call a bad line. But the reason why I don't like to just call it a bad line is because it's not that accurate in terms of, like, I just don't feel like that's the best way to understand it, because I get that you would call it a bad line because from the CPU's perspective, you're losing cycles. But I think the thing I don't like about it is that it describes the entire line, and it's actually not the case that the entire line is bad. You can, for example, create the condition that makes it a bad line a couple different ways, and you can create it at different points within the scan line, and you can also like turn it on and turn it off, that condition that makes it a bad line. And really all that that condition actually changes a few things in how the hardware works, but I can sort of get to that. But really what I'm trying to communicate there is that we can kind of control when this is going to happen and basically whether or not it happens. And yeah. So back to those scroll registers, I mentioned that the scroll registers sort of delay when this is going to happen or make it happen a little bit earlier. So all they actually do is, let's talk about this bad line condition and when it happens. So from me describing that it happens on character rows, you might think, oh, this happens every 8 lines. But there's actually a more specific definition for that is a little bit more useful in terms of us manipulating this to our advantage. So it normally happens every 8 lines, but when it actually happens, there's an internal register in the hardware that we call raster, and that just scans out. It just counts every scan line. So like around here is going to be about line 50 or so. Down here is line 255 or so. And the whole, so 50 to 250, somewhere around there. But the whole thing is that internal register just counts out the entire screen all the way down. It's actually 9 bits in order to count out all 312 lines of PAL. And then also 262 lines in NTSC. But yeah, the important part is that there's that raster thing. And so you have the scroll register as well, which is just 3 bits of one of the other settings registers. And so the condition is actually when the lower 3 bits of the scroll register match the lower 3 bits of the raster register, then we have a bad line condition, right? And so by changing the value of the scroll register from 0 to 7, which is a 3-bit value, we sort of change which every 8 lines that it runs that off of. But really, it's just that simple comparison, right? And in hardware, that simple comparison is not like a software we would think of an if, where at this one point in time, we're going to check this value. But in hardware, this is kind of a continuous thing. So every clock cycle, this basically gets updated with whether or not this condition has occurred, right? Now, the important thing here to realize is that this allows us to, from software, either create or prevent a bad line condition, not only for whatever lines we choose, but also at different points in the different lines we choose. Because we can write that scroll register to be anything we want at any time throughout the screen, so long as the CPU has access to the bus. Does that kind of make sense? Because now we're going to get into sort of the meat of this. So the interesting thing is that there's a lot of additional sort of tricks that you can do with this. Let me pull up one of these because it's kind of easy to show on its own. But yeah, I really want to hammer, and this will make more sense later, that I don't like to call them bad lines. I like to call it a bad line condition. Because again, we have a lot more control over it than just which lines it happens on. We also have different parts of the line that it happens on. That's actually really important to understand some of the hardware tricks that we can do with it. So I should have here a test project of mine. And what's interesting here is you can see that it smoothly scrolls the entire screen down. Right? Now, I mentioned, of course, that the scroll register is only up to 8 lines, so it would only be able to move the screen down about 8 pixels. So one way this could work is it sits there and just moves it, and then when it gets to 8 pixels, it'll take all the screen memory and shift it down one row, and then it'll restart the scroll register. So the scroll register will sort of keep scrolling 0 to 7, 0 to 7, all the way down until a certain value, and then it will scroll the other way, and it's going to be shifting the memory all the time. But that's actually not what's happening here. What's happening here is so normally the bad line condition, like the hardware sort of designed so that you would, during parts where the graphics aren't displayed in the frame, you would kind of set up the scroll registers to have the screen be where you want it, and then you would leave it be and just let it scan out how it normally would. It was never really designed to be able to do things like changing those registers every scan line, but of course we can still do that, right? And so what we actually do here is we know about when the first bad line would occur based on the scroll registers. But right before it does that, the line before we do that, we actually adjust the scroll register. So the next line, instead of having the bad line condition, that won't happen. Yeah, I'll do that, Love Like Semtex. It might make it easier to talk about scan lines anyway. They moved these around. I think that's it. Yeah. But basically, my point is that if we know where the first bad line condition would happen, we can kind of change the scroll register every line until we sort of allow it to happen. And so we kind of delay the bad line condition from happening when it normally would. And then at the end, we sort of let the screen scan out. And by doing that, we're able to sort of delay the display of the entire screen, which is actually really interesting. And all we've actually done is just change the scroll register every line so that that bad line condition, those 3 bits will never match until we want them to. And then as soon as they do, then the screen will scan out normally. So this is called FLD, which is it stands for flexible line distance, and it's one of the more basic tricks on the C64. Let me see if I can load this into this debugger and see if we can see it better here. By the way, the reason I'm totally into this stuff is because of tricks like this, because I find this so interesting. Let me mute the audio here. The little test track I was working on. I think it's this one. Not much we're able to see here, actually, because of the way that this displays. But we will see, perhaps here, the Y scroll is changing, because we can change that to whatever we want. We ended up changing it throughout different scan lines. I think here. I basically end up keeping it static while the I don't know if you can tell up here, this is kind of bouncing up and down. And on the areas where I'm delaying this, the Y scroll up here actually stays at a static value because we just keep it and we hold it at this particular value until we let the thing display. The gray area on the top, by the way, this little flickering area, it's really common when doing old school stuff to like increment the border color and then do a bunch of work and then decrement the border color again. And this basically tells you how much of your frame something is taking up. So in particular, this little area here, if I do this, the area there that's basically telling me how long it's taking to play the music into the frame. So it goes into the frame a little bit, and that's all that is. So you'll see that a lot on, if I pull up a lot of like test projects, you'll see that quite a bit because it's very useful for debugging. But yeah, so basically how this works is I wait until basically the first scan line. Let me pull up the code for this because it's not much code either. It's very much not a lot of code. I wait for a specific scan line. Actually, I have an entire table here where these are the scan line offsets. Just a big table of 256 values where I want the screen to start scrolling or to start scanning out. And I just wait for that initial scan line. And then throughout the point where we're not... How do I do this? Okay, yeah, so I wait until we're on the next scan line, so I just start scanning out as fast as I can. I wait till we're on the next scan line, then I compare it to when this value is, which is when we should let the screen start happening, because this will just scan out like this, and then whenever this is finally equal, then I'll stop adjusting the scroll register, but otherwise I'll just take whatever the normal scan line is and just stuff it into the scroll register, and that will keep the bottom 3 bits of the raster counter and the scroll register from matching for however long I decide to do that. And then eventually I'll just let the screen scan out. And I don't know if you can see this down here. There's a little bad line thing here that will say when that bad line condition has occurred. And it's moving around a lot because of this FLD thing, but it sort of makes sense. Let me pull up again the witchcraft thing. because I can kind of show you when those bad lines are happening. So this should hopefully just start or not. Do this again. So if we go back here, so I don't know if you can see the grid of characters here, but every 8 lines you'll see that there's a bad line condition. If you can kind of see the bad line thing ticks on as I scroll down here. And that's because we're not really manipulating the scroll registers. But then something funny happens when you get into this display area. First of all, the graphics are going to go nuts, but just ignore that for a second. I think it's... Yeah. This very first pixel in here, I cause a bad line. And then there's no other bad lines until the very end, which is kind of interesting. There actually are bad lines, but they're happening at the end of the lines, which is out here, and only on certain lines. But before that, they're just kept turned off because of the way that this hardware trick works. But let me see if I can describe this. So basically, internally in the hardware, there's a few internal registers that will sort of see that this normal operation happens. The main one is this thing called VC, which is a 10-bit counter. There's a VC base, which these registers will kind of swap values under certain conditions. And then there's RC. So VC is basically where in the video matrix that this internal pointer is. So there are 40 by 25 different character positions. And initially, they basically start at 0. And then what will happen is that every scan line, when the bad line condition happens, or somehow there's a few conditions here. So at some point outside of the display area, so sometime out here, we don't know when, and it doesn't really matter when, VC base gets set to 0. And so that means, yeah, we'll get to why that's important. Then on the first phase of cycle 14 of every line, and we're talking about every pixel line, VC is loaded from VC base. So we take VC base and we put it into VC. And then there's some other stuff that happens. And then if there's a bad line condition while this is happening, RC is set to 0. So RC basically counts out which pixel line we are in every character. So it'll start at 0 and then it'll count up to 7 and then it'll go back to 0 again. But the important thing is that this VC base goes into VC at cycle 14 of every line. So basically VC will get incremented and it will display out the different characters here. So that's basically what it's using as the index. And then VC will be reset to VC base every line. So that's why all 8 pixel lines here will display the same characters, if that makes sense. They'll display different graphics from those same characters, but they'll display the same characters because it's being reset every time. And then later, in the first phase of cycle 58, if RC is 7, which means we're on the 7th pixel row of that pixel line of the character line, then VC goes back into VC base, so it sort of feeds back on the 7th line. So the next one, it'll be reading the next characters for the next row. And so you have this sort of feedback with these two values. I wonder if I can do this with like pseudocode. So we have something like sometime outside of display area. VC base is 0. We'll do this assignment syntax. And then we can have like our pixel line loop, right? Because then this basically happens all the time. And so we can actually do something like this, So we'll have this sort of forever loop. And then we'll have a cycle counter for each line. So we can say like for line cycle in 0 to 63. Then if line cycle is 14, and I'm simplifying a bit here because there's a bit with the higher low phase, we say VC gets loaded from VC base. And we'll have some other things here too. The first phase, cycle 14, VC base, and VMLI is cleared. We'll get to VMLI in a second. If there's a bad line condition, RC is also set to 0. Something like this. By the way, guys, thanks for putting up with me just wanting to talk about this stuff. I know it might be hard to ground some of this information, but I find it really interesting because this is something that I've wanted to understand for a long time, and now I finally feel like I have a good understanding of it. But I'm just realizing as I'm explaining it how much assumptions have to be, like how much I have to assume you guys already know to be able to even talk about this properly, which is kind of the issue. But yeah. So we can do something like this, which is, I mean, this is basically a continuous value because of the hardware, but we can sort of think of it like this being reset every line. So we can say if y raster and 7 is equal to y scroll, and y scroll is only 3 bits. But we can do this anyway to make it clearer. So every cycle we have whether or not we have a bad line, but again this happens, yeah, we can say that this happens every cycle on every line. So actually we'll do this for line in 0, 312, assuming PAL. Actually we'll do raster like this. Then it makes a little more sense. To match the names here. I guess kind of seeing the picture I'm painting here, though, is that there's basically some very simple states. Maybe if I sort of continue to transcribe it like this, it'll make more sense. I'll be able to sort of describe this in a simpler way. But what I'm trying to describe basically is that these 5 rules here describe an interaction between just a handful of registers, like 3 or 4 registers, that basically describe all of how the video hardware works. I mean, there's some more details about accessing and stuff, but the important thing here is that we can actually derive how like all of the important hardware tricks on the C64 work from these very simple rules. And that's what's actually really interesting about this. So here's something else. So if the cycle on this current line is between this range and it's a bad line condition, we'll do it this way. We'll just sort of do this. So actually, it's actually something like this. So BA is the bus access signal for the CPU. So we have one C-axis done in the second phase of every clock cycle in range 15 through 54. Read data stored into the video matrix color line of the position specified with VMLI. This data is internally read from the position specified with VMLI. So GX display state. So the important things here is that we're going to do something like this. Say the video matrix, or how do I do this? We can say the video, which is going to be our internal video register. So that's going to reset to 0 as well. I think that actually happens. Maybe that never gets reset because it wouldn't have to be. Oh, guys, thanks for bearing with me. Well, I just want to talk about this stuff. So we end up with something like this. With some value. This actually comes from VC. Or we'll call this screen mem. We can call this video buffer. Video color buffer even, because it's actually both. These are 12-bit. So we can actually think of it like this. So this is if there's a bad line condition, this happens. There's another couple things here. CX is done the second phase. Where do the GXs happen here? And then we have VC and VMLI are both incremented. So yeah, so we'll do the C-axis is here. There's a G-axis. And we can basically, we'll call this display. Like that. And then, yeah, so this actually is sort of making sense here. And then this is the last bit here. And there's just some really cool stuff that's going to be happening based off of this. And then VC. It's something like this. think it's actually, this is a pretty good way to describe this here. Whoops. Do this. So it's roughly something like this. Roughly something like this. There's a couple more details about where it's indexing. But this is basically how the hardware works. So at some point, VC base is going to be reset to 0, which means it's going to be reading from the top left of the screen. And then every pixel line, a couple interesting things happen. If the raster matches the scroll, the lower 3 bits, then we get a bad line condition. And at any time during this, if there's a bad line condition, the video will be brought into display mode. And I'm assuming that video is in display mode for a lot of this stuff, but it really doesn't matter that much to know the difference there. Just know that it will be displaying stuff. If we get to the 14th cycle on every line, VC base gets loaded into VC, and this VMLI, which is sort of an internal counter, gets set to 0. And then what happens is that we might steal cycles from the CPU, but then between these certain scan lines, if we have a bad line condition, we're going to be reading in screen memory and color memory, which will give us the colors at these positions and also the screen data at these positions. Note that in bitmap mode, the screen memory actually determines the second and third color for every block. And then the bitmap, the G data, the graphics data, will actually determine the graphics that's there. But in character mode, it's all character indices and then the color for each character. But the important thing to know there is that it's going to read the same data. It's just going to interpret them differently, depending on the mode there. But yeah, it's going to read out this. Only if there's a bad line condition, it's going to do these C accesses here. Or this is per cycle, so it's going to do a C access within this range of cycles if we have a bad line condition. Regardless of if we have a bad line condition or not, it's going to read out this color buffer here, indexed by this VMLI, this index here, into display, which I just call the register that'll just scan out each pixel over the next 8 display cycles. Not that important, but can you kind of see a picture that's being painted here? I think this will be a little more clear for you guys who especially watch my emulator stream, because this is kind of how you would write this in an emulator. So then, yeah, so each cycle here, we're always going to read in new, or if we have a bad line condition, we're going to read in new stuff into this video color buffer that's internal. And then regardless of whether or not we do that, we're going to display the next position here. And then we're going to increment these pointers. So VC is going to increment where we read that from, and then VMLI is going to increment where we're storing that in this buffer and we're reading from this buffer. What's interesting with this logic here, and this is actually kind of important, VMLI will always get reset to 0, and VC will always get reset to VC base on cycle 14 of every line. So that's going to happen somewhere out here. And so it's going to end up scanning out the same VMLI from 0 to whatever the entire time. It's also going to end up scanning out the same VC values throughout the screen here on every line, because VC gets reset to VC base every pixel line, right? Except for when the cycle is 58, which is somewhere around here. It's actually a little bit sooner than that due to the way that this scans stuff out. And then the row counter is 7, which means we're on the 7th pixel line of the display here. then it's actually going to turn the display off. And then at this point, it's going to feed VC back into VC base. So VC starts at VC base and then scans out and just keeps incrementing at every one of these 8-pixel blocks. And then at the end of the line, nothing will happen except when the row counter 7, at which point VC will feed back into VC base. So that at the start of the next line, it's going to display the next bit of characters. Right? However, there's a couple interesting things to note here. It's actually possible to re-enable the display at the end of this. Also, there's one thing here that I forgot. Oh, no, this is actually correct. Cool. So it's always going to scan those out. And then the other thing here is that it only actually reads into this video color buffer on the bad lines, or when there's a bad line condition within these cycles, I should say. And then this actually, the contents of this end up staying constant throughout the other lines of that character row, right? So as it sits there and scans out the same VMLI for the next 7 lines, it's going to be reading out this same data every time, but then displaying it in different ways depending on the video mode and stuff. But so at the end of the 7th line, if RC is 7, so that's the end of the 7th line, and cycles 58, it's going to basically turn off the display, this whole mechanism, and then, or not all of it, but it's not going to display. So it actually really just this part here, how it displays the data, is really all that this mode actually determines. But then, it's going to feed back VC into VC base. And then at any cycle after, and I think this includes 58, it might be after 58, if the mode is in display mode, then it's going to increment RC. So under normal operation, the first line of the display, we're going to have a bad line condition because these are going to match. It's going to put the display into display mode, where normally it starts in idle mode. On the 14th cycle of that first line, it's going to reset these. And there's a bad line condition, so it's going to set RC, which is our row counter, to 0. On cycle 12, which I actually should perhaps move this above here, because we have a bad line condition, this bus access to the CPU is going to be set low, which means we're telling the CPU to stop. A couple cycles later, we're actually going to start doing our reads. So if we have a bad line condition, which we do on this first line, we're going to read the next value into our video and color buffer, which we get from color memory and the screen memory. And then we're also going to output that value from the same cell in that register. And then we're going to increment the counters we use for those registers. So that's that first line. And then what's going to happen at the end of that scan line is this, which is that we are in display mode in cycle 58, so then we're going to increment RC. And then the whole thing happens again for about 7 lines, except on the other lines, we're not going to have the bad line conditions, so we're not going to have the C accesses, but we're still going to have the G accesses with the graphics data every other line. Now on the 7th line, a couple things will happen. So RC, because it hasn't been reset, because we haven't had the bad line condition on other lines, because raster is always counting up, RC is going to end up being 7 on cycle 58, and so then the mode is going to be switched to idle mode, and then VC is going to feed back into VC base. So that on the next line, VC can start scanning from that new value, and then it will scan out the same ones every time. In addition, because the mode goes into idle, RC will not be incremented there. RC will just stay at 7. However, on the next line, under normal operation, all this stuff will happen again. So RC will get reset here. It'll do more C accesses to refill this buffer, et cetera, right? So here's where it kind of gets interesting, right? There's a couple things we can do that will sort of make this a little bit more interesting. So if we, for example, scan out the first row of characters, so if we just let the bad line happen, the first bad line, and we wait till like the 8th cycle in the display area, or sorry, the 7th line, the end of the 7th line, here's what's going to happen. On cycle 58, RC is going to be 7, and then the graphics mode is going to be set to idle, and VC base is going to be reloaded into VC. However, if right after that, we actually cause a bad line condition by manipulating the Y scroll so that this will match, In fact, I should also put this down here. This actually happens anytime throughout the line, but it only really matters here. So if we adjust Y scroll to happen right after this, or sorry, right before, yeah, right around cycle 58 here. Yeah, after this. So VC, let's see. How do I want to describe this? My point is there's a couple tricks we can do. And let me actually describe some of them in the order that might be simplest here, right? So normally we would just set the scroll register to something at the beginning of the frame and it'll let the character scan out normally. But what if we wanted to, for example, hold this RC thing? What if we wanted to re-trigger a bad line condition every line? So what that would do is it would display this first character row throughout the entire screen. So what we could do is we could just adjust the Y scroll every scan line so that this bad line condition is going to happen this entire time. So what will happen here is a couple things. First of all, we're going to lose 40 cycles because the CPU, it's going to need to steal those cycles for reloading this buffer every time. But the interesting thing is that RC will never end up being equal to 7 because it's going to be reset to 0 every line. And yeah, so it will actually, here on cycle 58, it will actually increment RC, which means it'll go to display the next pixel row. But then on the next line, because we had a bad line condition on cycle 14, because we're recreating bad lines the whole time, then RC will be reset to 0. So at the end of the line, it will actually increment to 1, but then on the next line, it'll be 0. So it'll just keep going in that little loop. So effectively, this will always be 0. Also, VC will never feed back into VC base, so we'll always display the same graphics over and over again. So it's always reading and displaying the same lines. But basically, all we have to do is manipulate Y scroll so that we always get a bad line every line, and then it will just sit there and it will display this first line over and over and over again. Right? And so that's sort of one of the basic stretchers that we can do. Now, this is really interesting because all we've had to do is just manipulate this one value, but we've sort of affected these internal registers. Particularly, we've held RC at 0 as sort of the most important thing we're doing there. And then we're also having it reread this video color buffer every time. So what's interesting here is that we can actually change some of the other registers so that when it actually goes and reads the screen memory, it doesn't just read it from VC. There's a couple offsets and stuff that it will do. Like you can change where screen mem is actually taken from, for example. So in addition to changing the Y scroll, we can also change which bank the Vic is seeing, and we can also change where it's reading the screen mem from. And then we can get it to do some really interesting things. We can basically get it to display any of a given set of scan lines however we want. And we can get some effects like, let me pull one up because there's a really good example of this. Here's a little demo that shows this. So the stuff on here, this is sprites, ignore those, but just watch the background effects. So basically how this works is there's a bunch of these scan lines of different graphics that are basically pre-calculated. So it looks like there's a bunch of parallax bars, but really there's only just a bunch of, I think it's 2 scan lines. This is repeated this whole time. And each one just has like these bars drawn in sort of 1D. And then it scrolls enough till it looks the same again, and then it just restarts. Right? And so this is done by basically doing this whole thing here by causing a bad line condition. I think it's actually every other line is the way they're doing this. And that would let the first 2 pixel rows of the character graphics scan out, and then it'll just reset. So it'll end up reading from the same position again. But remember, we can change where screen mem is located, so we can choose which sort of graphics lines are done. Now, in this case, if you wouldn't actually have to change that, you just cause this to scan out every line like this. But what's interesting is that if we move forward a little here, it starts to wave. And the way that that's done is that we can change where the screen memory is pointing every scan line that we're going to reset the scanning, if that makes sense. And so instead of just having it scroll, which is like sort of changing between frames, between lines, we get different versions of the scrolled image. So we get this kind of nice effect. So how many people have I lost here? It's a really good implementation of this, by the way. fact, let's do this. Let's even download this and see if that's where it's doing this. Good to hear, Love Like Some Text. If you ever end up in the Fuse office, by the way, and you wanna talk more about this in detail and ask questions, please let me know. As I'm just fascinated by this stuff right now, so I'd be happy to share. So I've never actually run this in a debugger before. We should be able to basically see what we expect, though, when we get to this part here. I'm just going to pause this in the emulator. I'm actually going to get a frame without the sprites because they're not very important. Pokey, yes, exactly. The copper is sort of meant to do this kind of stuff, but the Amiga hardware is a lot more configurable. So here we sort of have to trick the hardware into being able to display different things. But by the way, this is exactly what I expected. I'm pretty happy about this. So on the first line, we have a bad line. We can see the Y scroll is set to 3. On the second line, it's set to 5. 7, 1, 3, 5, 7. So it looks like the first line, there's a bad line, and then it'll let it scan out this first row of characters, including the bad line, and the second one. Let me actually do this, because I don't know where it stores this on the scan line, where it starts this. So it appears that it just increments the scroll register by 2 every time. And we get a bad line every other line. You can see down here, it'll say whether or not we're on a bad line. I'm just moving up and down. So this is a really good debugger for showing this kind of stuff. Yeah, I love it sometimes. I didn't prioritize the restart thing on there. That's fine. But yeah, so you can see here, because it causes a bad line on this first line, the row counter, which is RC, is at 0. And then at the end of the line, so we can actually watch this scan out as VMLI and VC scan out here. Eventually, the row counter will be incremented here on cycle 58 or so. And then row counter is 1 here. And then that gets scanned out, and at the end of this, it'll be 2. But on the next line, there's another bad line that's triggered. And so the row counter restarts, and we end up rereading the data again. But it's basically displaying these first 2 rows every time. Throughout the entire screen. And then by changing 2 registers, one's called D018, one is DD00, which is the charset and the video base. It can change which graphics it's reading. However, it only ends up changing. Oh, it looks like it changes the screen memory here, by the way, in order to get the different dithered lines. That I didn't expect, but that makes sense, because then it would be able to do waves on a per scan line level rather than every other scan line. But yeah, so all it has to do is basically update those same registers so that it reads the screen memory from different places every other scan line, and then it's just going to rescan out so those first 2 lines. And that's really all there is here, which is exactly what I expected. But it really isn't more complicated than that. A lot of the tricks you'll see on the C64. So in this particular case, the goal was to sort of hold RC at 0 or 1, for example, and then just reset it. And so that's one way that we can sort of control this, just by adjusting the scroll register. Now, another way that we can do it is, let's see. So that was holding RC at 0, basically, or scanning it to 1 and then resetting it to 0. So 0, 1, 0, 1, 0, 1. And that was basically resetting RC with a VAD line condition, so resetting it to 0. Another interesting thing we can do is we can actually hold RC at 7. Now, I don't know of any place where this is used, so it's hard for me to pick out a demo where this could be used. But the idea is basically the same, actually. That by either causing or not causing a bad line condition, so either causing or preventing one at a certain point within the scan line, we're able to keep something from happening. So particularly, we don't want a bad line condition on cycle 14, or else RC would be set to 0. So we need to prevent bad lines. However, there's another thing that we want to do here, because RC is going to be incremented if mode is display on cycle 58. So we need to somehow get mode out of display mode. So what we can do is, first thing we have to do is we have to start normal character display, because that's the only way that RC will ever get to 7. We can only reset it and then have the video hardware increase it. But once it's at 7, we can hold it there by doing this. First of all, on cycle 58, if RC is 7, the mode will be changed to mode idle, right? But then after cycle 58, we can cause a bad line condition that will take the video display out of display mode. And as long as we don't have a bad line on the next line, which would reset RC, then the last line of characters there will end up being displayed again, because RC never got incremented, because after cycle 58 here, I think this actually happens on 58. So I think I actually need to write this a little bit differently. I think I need to write this like this. Right, does this make more sense? So on cycle 58, if cycle is 58 and RC is 7, the display mode goes into idle, and then VC feeds back into VC base. But then this mode setting here is actually overridden by whether or not there's a bad line condition. So if there's a bad line condition, the mode will actually come out of that into display again. And then if the mode is in display mode, RC will increment. But maybe there's... I think it's this. Yeah, and then so the idea then is that on the 7th line after cycle 58, we do this particularly. Okay, I think this is it, and there's a reason why we need all this, and the reason I moved this in here has to do with the next trick I want to describe. But again, so we can either have it scan out bits of the character and then restart. For example, we can have it hold RC at 0 by causing a bad line every line. We can cause a bad line every other line, which will make it display rows 0, 1, 0, 1, 0, 1. We can do that all the way through like 7. We can do 0 through 7, 0 through 7, 0 through 7. When we do 8 lines, it's a little more complicated, and I'll get to that. But we can also have it hold on that 7th line. We can't hold it on any other line because there's no conditionals that say like if VC is 3. And changing the scroll register every line wouldn't do anything, because that only affects whether or not we have a bad line condition, if that makes sense. So we can't just like repeat the 3rd line over and over again. But we can do the 1st line over and over again by, again, holding RC at 0. And then we can keep RC at 7 by letting this happen. So on cycle 58, when RC is 7, we'll let the display go into idle mode. And then if it's in idle mode here on cycle 58, RC will actually not increment, because this only happens when it's in display. So after cycle 58, we can cause a bad line, which will bring the display mode out of idle mode, right? So it's in display mode again. And the interesting thing here is that because we've skipped the increment of RC will stay 7. And as long as we don't have a bad line condition on the next line, which would cause some bad stuff, it will just keep displaying line 7, right? As long as we keep creating these bad line conditions at the end of the line. Now, the reason why we actually have to do this, because it looks like we wouldn't actually have to do this and RC would still say it's 7. That's actually true, that RC would still be held at 7, but we need to have the mode be in display mode on the next scan line for it to actually display the row again. Otherwise, it'll be in idle mode and it won't actually display any characters. It will display some kind of data, but I'm kind of hand-waving over that. So that's how a trick would work that would repeat the 7th line. And then again, we have the same sort of condition that if we change where screen memory is located, or sorry, not screen memory, but like the character set, for example, in character mode, we could actually, be able to select different lines to display by holding it at that 7th line. Another interesting thing that happens, though, when you do this is that VC is always feeding back into VC base, because this happens on the 7th line, but we're making the 7th line happen over and over again. So the screen will actually scan through the different characters really, really fast. Now, we're not reading any more color data because we're preventing bad line conditions. But if we were to do this, for example, if we were to wait till RC is 7 and then start causing bad line conditions on all the lines after that, a couple interesting things would happen. So we would basically we would want to cause a bad line condition for it to read new data, and then we would want to prevent a bad line condition between cycle 54 and 58, so this wouldn't happen, and then RC would stay at 7, and then we would want to cause the bad line condition before the next line again. And then we could get it to refill this buffer, but VC base is feeding back into VC 8 times as fast as it should, and we get something called line crunch. Let me see if I can find a picture of this, because it's basically only displaying the 7th line of all these graphics over and over again. So I don't know if I'll be able to find a picture of it. Probably not. By the way, there's a website called Codebase64 that has a lot of these routines here. Here's a binary of this. And they have a lot of source code to it, but the thing is that they don't really go over how it works. They just kind of show you the code and say, oh, the timing's tight on this one. It's like, well, that's not helpful. But with this extra information, it actually is really helpful, because you can sort of see where the timing is that happens. But let me pull this up. And pull up a thing here. So this is what line crunch looks like. You can see what happens here is it enables the line crunch on the 7th line of this line of character graphics, and it just keeps doing the line crunch. So it basically repeats the 7th line. But then when it stops doing that, it lets the stuff scan out normally after that. I'll get to that in a second, Luigi Mario. So this will display, this will repeat the 7th line here, and then eventually it'll stop doing that, and then the characters graphics will continue to display new lines after that. But because VC and VC base has kept increasing really fast, you'll notice this screen starts to wrap around here by the time it gets to these other lines. That's actually what's happening here, and it's shifted as well. So that's, you can see this is the stretching effect, but then because VC kept feeding into VC base, it skipped way more rows than it should have, and then we get this screen displayed again down here. So kind of interesting, but that's sort of another one of the hardware tricks we can do. And if we look at I think it's the Vic programming, and there's something here, the hardware tricks. There's an introduction to vertical tweaks article on here, which is really interesting because I basically described a lot of these now. So bad line delay is that FLD thing, so we can basically delay when that happens. Repeating the last line is the one that I just described. Every line is a bad line is the one I described before. Repeating the first line is basically the same thing. And then there's the repeating char line, and this is the one I've actually been using in a couple demos. And the way it works is actually really simple. So what we do here, actually before I describe that, I'll answer your question, Luigi Mario. New episodes will be published on YouTube. I have missed publishing the last couple of them. I have a note to do that. I'll probably do it tomorrow. But yeah, I've just been a little lazy on publishing those. They're actually uploaded. I just haven't filled in the descriptions and the tags and stuff and then made them public. So yeah, that is the plan. I've just been a little lazy about the last couple. So sorry about that. Anyway, so this last hardware trick, let me pull up my demo again because it actually uses this. Here. So what it does is we want to basically prevent any bad lines. And what we're going to do is we're going to have the hardware, let's see if we can do this. We're going to have the hardware read in all of the character and color data. So it's going to read in black for all the colors, and then all the characters are going to be whatever the scroller has. It's going to read in all of that data on this very first line. And then for the other lines, we're just going to change the char set to say like which of this different 8 scan lines of the font we're going to display. And then we just want it to keep displaying that same character memory here. So we only update this first row of character data, and then we only read it on that first line. Then we want it to just keep displaying lines of that over and over again. And so the trick is to have it do this trick where it'll just repeat the same character line over and over again. And the way it works is actually pretty simple. So we let the first line, we have a bad line, and that's when it's going to read in all of this video color buffer. Now at this point, I actually have it set to a character set that's actually completely blank. So this actually happens on this first line here, which is just black. I could have it display this first scan line, but I actually want to not necessarily display the first scan line here. So I just have a black border there and have it read in all the character data. And then on the next lines, on the 22 lines after that, I have it actually doing this hardware trick. So for most of the lines after this initial one, and this initial one, it's going to read in all the data. And then on the other lines, most of them we don't actually have to interact with the hardware to actually trick it in any way. But on the 7th line of each character, we actually do need to do something special. And the reason is, the thing is that we basically want RC to count up to 7 and then reset back to 0 and count up to 7 again, just over and over again. And we don't want to cause any bad lines during this part of the frame because we don't want it to, or this part of the lines because we don't want it to read any new data. So we can't just have like every 8th line we do this so we reset it to 0, because by the time, if we were to do that, if we were to cause a bad line condition around cycle 14, we couldn't uncause the bad line condition before it will start reading data because of this logic. So that's not going to work. So what we can do though, and then also normally when RC is 7, it's going to change the display out of display mode, which means RC will not be incremented. It's just going to stay at 7. So somehow this is the thing that we want to disable. We want to disable, actually it's this one that we want to disable. Here, where it goes into idle mode. That's particularly what we want to disable. Now I think I wrote this wrong again, very slightly wrong. I think it's actually this. Bear with me about some of the details here. But I think it's actually this. So on cycle 58, if RC is 7, the display is going to go into idle mode, and then it's going to load VC base into VC. And then after that, I think is what this article says. I think it just says after. What does RC? Yeah, if the video logic is in display, say afterwards, RC is incremented. Now this is actually the really important thing here, is that here on cycle 58, and when RC is 7, we have the mode going into idle mode. But on cycle 59, or some cycle after that, RC will be incremented only if it's in display mode. So at some point between just think about the logic here, because there is a little bit of oh, you know what? This is actually true. I had it right here. Okay. And I'll explain why. Sorry about that. So basically what happens here is on cycle 58, if RC is 7, the display is going to go into idle mode, and then VC is going to be loaded back into VC base. But what we can do is if we cause a bad line condition between when it's done doing the C accesses, so we've gotten the CPU back, but really we just need to not cause bad lines in this case during this time because we don't want any of these to happen. So it's sometime between cycle 54 or 55 in particular, because it's the one after this, and cycle 58. It's sometime between that. So cycle 55, 56, or 57. If we can cause a bad line condition, then what's going to happen is that this is still going to go into idle mode and then reload VC into VC base. But then because there's a bad line condition, right after that, it's going to go back into display mode. And then it's going to, because it's in display mode on this cycle, it's going to allow RC to be incremented. So on the 7th line of every character row, we need to cause a bad line within those 3 cycles, 55, 56, or 57. And that will allow this to happen. And then on the next line, we need to readjust the scroll register, so we only have to wait 7 lines before the next one. So it's actually not much. In fact, the code to do this is really short. It's here. Actually, it's here. I call it a stretcher loop, but it doesn't actually stretch anything. But it's right here. So if we're on the 7th line, basically, we're going to load one value in it, which will cause the bad line to occur one line before it would at the very end of the line. Otherwise, we're going to load this regular value. So every scan line, I actually write the scroll value, but every 7th line, I adjust it so that it will cause that bad line at the end of the line within those 3 cycles, and then that will cause that hardware trick to actually occur. And then again, we can select which line we display by changing character sets, because the different character sets represent the different lines of the font, right? And so that's this repeating char line effect. Now, the reason I use this one in this context is for a couple things. First of all, this will allow VC and VC base to interact normally, right? So if we were to repeat during this display area, if we were to repeat the first line of every character, we would still get that sort of stretching, and we'd still be able to change the registers that we need to every line to be able to get the effects that we want. But VC base will end up never being updated during that display area. And so what would happen is that when we sort of let the display scan out normally again, there would actually be a few lines of empty data before this would happen again. Otherwise, we'd have to adjust the original graphics so that this data for the rest of the picture is actually up here, if that makes sense, because we're going to trick the hardware during this period, and then here we're going to sort of re-enable display, and then we'd have to sort of adjust the graphics data accordingly. So I didn't want to use that trick. We could do the one where we hold RC at 7 and repeat the 7th line, but then we have the opposite problem that VC base is incrementing every line. It's being fed back with VC every line, and so then it would actually skip a bunch of graphics, and so we would have to like overwrite the top graphics here to contain this data somewhere around this point in the frame. So we'll let it display that, and then we'll overwrite it, and then we'll do a hardware trick, and then at the end of that, and that would just suck. The other downside about that is that the first 7 lines of the character stuff, we would have to have the hardware scan those out first and then start doing the 7th line. And so that isn't really ideal either, because we have graphics all the way up until this display window. And so this hardware trick is really nice because we can start doing it basically immediately. And then also other than the fact that it's displaying the wrong stuff, the hardware is mostly working the right way internally. So as soon as we stop, we can have the rest of the hardware sort of scan stuff out normally. And other than the fact that we actually changed display mode here, which that's only to switch from multicolor bitmap to high-res character in order to display the scroller, there isn't that much that we actually have to worry about there. But that's that's basically the kind of stuff that I wanted to talk about. I wanted to talk about this in particular, is how this sort of video hardware works, and it's really pretty simple logic, actually. And it's really described mostly here. There's a lot more in this article here that's described, and it's literally called Vic article. If you search Vic article, you'll find this. So if you're an aspiring C64 coder for whatever reason, or just more curious about this stuff, this is a really good document to read. It's kind of heavy, but for me, who has been interested in C64 coding for a long time, this was a really cool read, especially after I was just sort of discovering how these tricks actually work, which was kind of, I've talked about it a couple times in other videos, but something I wanted to do for a long time, because like I said, I like these demos, and then only this last winter did I start actually digging into how effects work that actually use these tricks. This last summer, I actually was able to apply it for the first time, and then this last weekend, I was able to be able to weigh the different options of different kinds of the hardware tricks because I was able to understand them at this level, and I was able to pick one that would actually work in our use case, which was displaying the scroller area here within other graphics. And then I was able to apply it by only really doing as much work as we actually needed to do every scan line. So for me, it was actually pretty cool to understand this stuff. From talking about this, by the way, again, guys, thanks so much for just letting me indulge and just use the whole 2 hours just describing this stuff. I might actually, at some point in the future, like not making any promises, but just thinking about it, I might actually try to give a talk about this at some point and sort of lay out the information in a way that would actually make sense for people who didn't necessarily know how a lot of this hardware works. Or what to expect here. So maybe there's a way I can teach that better because I find it really interesting. And the other thing that I really like about this is that from a hardware perspective, the thing that you'll notice most is that these internal registers here, like they only really ever increment by 1 or get reset. So it's a really simple hardware design, which is really cool. Oh, cool. Love like some text. I didn't realize. Yeah, it's a really useful one, and it's just really interesting. Like, again, I really like hardware, and I like learning about this old hardware because it's often very simple. And when looking at it this way, like, this is really simple hardware. And with a couple other things that I glanced over, like the fact that this display thing there's a little bit of magic there. And then where it gets stuff from screen mem is also a little bit magical, but mostly it's pretty simple stuff. And I just find this so incredibly interesting. And yeah, these tricks were being employed by demo coders in the late 80s. Most of these were understood by then, and there's a few that I didn't go over as well. Like there's one called FLI, which allows you to basically read different color memory, but still have the same screen memory. Is that right? I'm not sure because I need to sit down. I'm talking about a trick that's called FLI, which allows you to, I believe, change I think you read different screen memory every line, but you display the same graphics memory or something. Because I think it was this. I think it's you stop this from happening. So you never reset RC to 0. But then you still will do these accesses, and I can't remember how that worked. But it was a way to get around a lot of the color limitations. I think it was this. I think you let RC scan out from 0 to 7. So it will display the bitmap graphics normally, but then you cause a bad line condition after that, so you still always read in new... Yeah, that's what it was. So after cycle 14, you cause a bad line condition. So you skip this, but you let this happen. So it's going to read in new data every line, in particular new color data, because that's how the screen memory is interpreted in bitmap mode. So it'll do this, but then you have an issue because then the bus access thing here actually happens a lot later than it should. So normally there's this 3 cycle window from cycle 12 to 15 where the bus access line goes low, and that gives the CPU some time to basically stop using the bus. And if that doesn't happen in time, so if you cause this bad line condition too late, this bus access signal will come up late. And then depending on the instruction you use, and I believe most of them actually have issues with this, because I think the CPU will basically access the bus every cycle that it's running in order to simplify the hardware implementation. What ends up happening is you get these glitches on the bus, and those end up being manifest as what's called the FLI bug. And admittedly, I need to look more into this because I'm not entirely sure what the exact details here are. If I just search FLI bug, I get a bunch of pictures that get around the FLI bug, but I actually want to show the FLI bug, which is you basically get these a few characters worth of just gray graphics at the left side of the screen. And you can do things like cover it up with sprites. Like here's an example of it, where these first couple characters here end up having to be covered by sprites because you'll get this light gray pattern out of the character, out of the character mechanisms, the character display mechanism. And then you can cover it up with these other gray pixels using sprites. But yeah, it's basically because you're glitching out the bus because the CPU shouldn't be accessing it, but it is for those first couple lines or the first couple characters where we're reading data from the screen. So that's kind of funny. But yeah, that's how the FLI bug, that's how the FLI trick works, I believe. And I don't know of any other tricks that use the character display that are really that different than these tricks. Because most of what you'll see is effects that use different applications of these tricks to do different things. So for example, the application of the repeating chars trick was that we could change which char set we're using, and then we're able to select which graphics line or something like that. You know what I mean? Those are kind of applications of these tricks. And so one of the things that I kind of don't like about a lot of the documentation that's on here is that like a lot of these are sort of presented as hardware tricks, but really a lot of these are sort of applications of the hardware tricks, if that makes sense. I guess this article is really good in that sense because it actually can kind of show you this, but it doesn't go into much detail. And it says stuff like, in this repeating char line, it says, does not seem to work in combination with the open side border. And that gives me the impression that whoever wrote this didn't understand why. But it actually is really obvious why when you look at it from this perspective. It's because I mentioned, I think, with the border stuff, that the way you sort of disable the border from being displayed, which is actually happening here, by the way. You get sprites down here and over here because this top and bottom border have been turned off. And the way you do that, again, is you have the character mechanism set to display 25 characters, which means the border will basically start here. And in the middle of that 25th character, you set it to display 24 characters, which really only adjusts where the border starts. But then because the border starts earlier than where it's actually drawing, it will never hit the condition that will turn on the border, because that actually happens at a specific point on a specific line rather than wherever. And so then that gets missed, and then the border is never turned on. Now the display stuff goes into idle mode, and it can never basically get out of idle mode because there's a scan line limit to where that will happen and where it won't. And I kind of ignored that in this description, but it doesn't really matter. But then it's still able to display sprite graphics down here. That was kind of a tangent. I can't remember why I brought that up. Oh yeah, because the side border thing. So the side border, the same trick works. There's another bit in one of the hardware control registers, which is whether or not it's going to display 40 or 38 characters. And the only difference there, again, is where the border starts. But in this case, it's horizontal. So if you can have it display 40 characters, and while it's displaying the last character, you switch it to 38, again, it misses that condition, and then it will not turn the side borders on. And so what's interesting there is that has to happen within a few cycles. And I think it was cycle 58 that happens on. I can't remember. I saw a timing diagram. I think LFT made one of these. Really great sort of companion to that Vic article. Basically, this is his timing chart, and basically none of this makes sense without understanding the Vic article because it uses a lot of the same names for registers and all that stuff. But there's really no new information in here that wasn't in the Vic article. It's just laid out in a really nice area. Well, actually, the sprite crunch thing is new, but that's something else. But I think it was here. Somewhere here. There's a border on here, 56. This V flag thing, wide, narrow. Yeah, because this is the cycle every scan line. And then it was here whether it's going to latch the border on or off here. And so, yeah, so it's right here. It's cycle 56 and 57. So here you have it set to be wide. And then on cycle 56, or yeah, I think it would have to be there, you set it to be narrow again. So it's like that one cycle window. Then on cycle 57, you have missed this, so the border doesn't turn on. But here's the problem. That repeating character lines, you have to write to that register between cycles 55 and 57. And so there's actually no way that you can write both of those within this 3-cycle window here, because this has to happen on cycle 57. And there's no way that you can get an additional write to one of these registers within these cycles here. And you can't write or you can cause a bad line before this, but as soon as you do it on 54, then the bus access signal goes high, and then you have other issues. So this is the only time that you can actually start writing any values, and you can't write that and also write this. So there's actually my point is there's a perfectly good explanation for why this doesn't work, and that's it. And articles like this at least are a step better than nothing, because they do describe the different things, the different ways that you can trick the Vic, which is kind of nice. But they didn't, like, I remember being kind of frustrated reading this because I didn't understand why this was tricking the Vic, why you could only display the first or the seventh line, or why any of that stuff. But once I discovered the Vic article, and also this timing diagram, which really helps sort of visualize when that happens. Because here you can even see where the byte fetches happen here. You can even see where the sprite stuff is happening in relation to that as well. Really, really cool stuff. But yeah, it kind of took a bit more reading with this Vic article. But it got me really excited. So I wanted to talk about this. Anyway, I think I'm done. If you guys have any specific questions about this or about our intro, about whatever, fire away. And otherwise, I am going to go play video games. But yeah, thanks again, guys, for hanging out while I just wanted to talk about this stuff. For those of you that enjoyed it, I'm really happy about that. For those of you who didn't, thanks for putting up with me. And I also hope this kind of gives an insight into why I keep wanting to do C64 stuff, because I find this stuff really interesting. Like, now that I understand this hardware, it makes me want to code more effects for it, because it's like, how can I exploit this in order to sort of prove my understanding to myself by making a program that proves that this works, that proves that I have this understanding. So if you guys see more C64 demos from me, it's because I'm excited about understanding this stuff. But yeah. I'm actually going to save this because this was kind of cool. I'm going to gist this up. There's that. Yeah, thanks, guys. Yeah, it was really dense. I hadn't realized, again, how much context you kind of have to understand this stuff, which is why I had to go through so much of like the basics in the beginning, and I don't think I did that in a very good order, because this wasn't planned out, which is fine. I don't think I want to do a demo on Vic-II. Vic-II has very similar hardware, but not quite as interesting. And a lot less memory, to the point where it's really annoying. C64 kind of hits this really sweet spot to me, where there's enough to do some really interesting stuff, especially understanding this hardware here. And then it's also limited enough that you kind of have to have this kind of level of understanding to be competitive, which I think is kind of cool. And Amiga can just do a lot of this stuff without having to trick the hardware. It's just so configurable that you have to set a lot more registers to make it do anything specific, but it can just do this stuff out of the gate. Whereas here you have to manipulate via Y scroll to have it kind of access different things. But anyway, thanks again, guys, and I will see you next time.